In this video, we're going to introduce critical numbers or critical points for a function and how to use them to find the local extreme values or local maximum or local minimum values of a function. So first of all, remember a local extreme value is a highest point or a lowest point on the graph of a function. So basically, it's a turning around point. Either the function is going up and then it turns around and comes back down, or it's going down, turns around and comes back up. Now, if it's doing this turning around in a nice smooth way, then it's going to have a horizontal tangent line at the highest or at the lowest point. But sometimes it could go up and abruptly turn around and have a sharp corner and come back down, or go down and sharply turn back around. In that case, it's still a turning around point. It's still a local max or a local min, but it's not going to have a tangent line at that turning around point. In fact, the derivative won't exist there. So that's basically what Fairmont's theorem says. So Fairmont was a mathematician who lived about 350 years ago, and he had a lot of theorems. This is only one of them. So he proved mathematically that if the function f has a local extreme value at the number c, then one of two things has to happen at c. Either f prime of c is 0, so it has a derivative there and it's 0, it has the tangent line is horizontal there, or the derivative doesn't exist at that number at all. So f prime of c does not exist. So this number c is a candidate. It's possible that it could turn out to be a turning around point. It might not be, though. Not always do these numbers turn out to be turning around points. But these are the only places where we could have a turning around point. So we call them critical numbers. So this number c in Fairmont's theorem is called a critical number for the function f, or sometimes we just call them critical points. So a critical number or a critical point for a function f is a point where the derivative is 0 or the derivative doesn't exist. It has to be in the domain of the function, though. Okay, so f of c exists, but f prime of c might not. Let's look at some examples. Let's look at f of x equals the absolute value of x. Let's pretend we don't know what the graph looks like and we're looking for local extreme values or turning around points. So the first thing we're going to do is find the critical points, and then we'll test them to see if they turn out to give us extreme values. So to get the critical points, we have to differentiate the function. And remember, we had to use the definition of the derivative to find the derivative of the absolute value of x. We found that it was the absolute value of x over x, or if we write it as a piecewise function, that's -1 when x is a negative number and +1 when x is a positive number. So notice the derivative is never 0. It's either -1 or it's +1. But also notice the derivative doesn't exist at x equals 0. So f prime of 0 does not exist. So that means that we just have one critical number. So x equals 0 is the only critical number. And to test it, we use a Sine diagram. So set up a Sine diagram for the derivative function, and you plot all the critical numbers on the number line. So x equals 0 is the only critical number here. The derivative doesn't exist there. And we know the derivative is negative for all x less than 0, so we put a minus sign there. And the derivative is positive for all x greater than 0, so we put a plus sign there. And we can see clearly the derivative changes sign at x equals 0. So the function is going down and then going back up. So we do have a local minimum at that number 0. And when we graph it, we can see it. There's the lowest point is at 0, 0. All right, let's do another one. Let's do f of x equals x cubed. So we want to find any local maximum or local minimum values of this function. So first we look for the critical points. We take the derivative. F prime of x is 3x squared. Now notice that f prime of x is only 0 when x equals 0, and it exists for all x. There's no place where the derivative doesn't exist. So the only critical number is x equals 0. So let's do the Sine diagram. So if we plug in any number less than 0, any negative number, plug it into the derivative, 3x squared, and you're going to get a positive answer. So the derivative is positive when x is less than 0, but also the derivative is positive when x is greater than 0. So there's no change in sign. Even though the derivative is 0 at x equals 0, it doesn't change sign there. So f of 0 is neither a local max nor a local min. So it's not a local extreme value. And if we look at the graph of f of x equals x to the third looks like that. It's always going up except momentarily at x equals 0. There is a horizontal tangent line there, but it's not turning around there. So that's what critical numbers are. They're candidates for local extreme values. They don't always turn out to be local extreme values, but you can check using a Sine diagram. All right, in the next video, we'll look at how to find absolute extreme values if your function is on a closed interval. And I'll see you in that one.